Let's look at an example here of calculating the centripetal acceleration components. A car travels at a constant speed of 30 miles per hour or 13.4 meters per second on a level circular turn of radius 50 meters, as shown in the bird's eye view. What minimum coefficient of static friction, μs, between the tires and the roadway will allow the car to make the circular turn without sliding? Use Newton's second law. So the net force acting on the car in the radial direction is the force of static friction toward the center of the circular path, which causes the car to have centripetal acceleration. So you can see this from the two diagrams. You see diagram A shows the force in the direction of centripetal acceleration, and then we can see by our free body diagram of the car the normal force, the weight or mg, and then of course the force of centripetal acceleration. So if we go back to our force equation here, force centripetal is equal to mass times the acceleration centripetal, which equals the mass times the velocity squared divided by the radius r. And we can set that equal to then the frictional force that actually keeps the car from sliding off the outside of the track. And that is our μs times the normal force. So if we sum all of the forces in the y direction, that equals the normal minus mg, just like we've seen before, and that is in the y direction, so it is not in motion, so we set it equal to 0. It's in static equilibrium. So then if we solve for n, the normal force equals the weight of the car, mg. So if we go back to our relationship, the mass times the velocity squared divided by the radius is equal to that force of friction, static, μs times n. We get μs is equal to the weight of the times the weight of the car, mg. So if we solve then for μs, the first thing they ask us for, what is the minimum coefficient of static friction? It's equal to the velocity squared divided by the radius times the acceleration of gravity. So we drop our values in here, 13.4 meters per second, all of that squared, 50 meters times 9.8 meters per second squared, we get a coefficient of static friction, μs, of 0.366. The value of μs for rubber on dry concrete is very close to 1, so the car can negotiate the curve with ease. If the road were wet or icy, however, the value of μs would be a little lower, or 0.2 or lower. Under such conditions, the radial force provided by static friction wouldn't be great enough to keep the car on the circular path, and it would slide off on a tangent, leaving the roadway. So now, instead of a flat surface, let's look at a banked surface. The Daytona International Speedway in Daytona Beach, Florida, is famous for its races, especially the Daytona 500, held every spring. Both of its courses feature a 4-story, 31-degree banked curve with maximum radius of 316 meters. If a car negotiates the curve too slowly, it tends to slip down the incline of the turn. Whereas if it's going too fast, it may begin to slide up the incline. So it's a balancing act. Find the necessary centripetal acceleration on this banked curve so that the car will not slip down or slide up the incline. Neglect friction. So we first find the centripetal acceleration. So let's study the diagram here a little bit. We've got our free body diagram. The normal is off at some angle, which is 31 degrees, and we've got our force of the weight, mg, straight down here. So we look at our free body diagram minus the car, then we've got n cosine theta, mg, and n sine theta as all of our component forces. So if we sum all of the forces, we let them equal to the normal plus mg, and let that equal to the mass times the acceleration, because we do have some movement here. If we sum only in the y direction, though, n cosine theta minus mg equals 0. So we're looking at only that up-down relationship. So n cosine theta is equal to mg, and n, the normal force, then is equal to mg cosine theta. The force centripetal then is equal to n sine theta, which equals mg sine theta by cosine theta, which gives us mg tangent theta. Remember that identity? We've used that before. Mg tangent theta. So the centripetal force is equal to ma centripetal, mass times acceleration, centripetal. Solving for acceleration centripetal, that's equal to the force centripetal divided by the mass, which equals, now we can substitute that mg tan theta in there, divided by m, the m's cancel out, we have the acceleration of gravity times the tangent of theta. So 9.8 meters per second squared times the tangent of 31 degrees gives us an acceleration of centripetal 5.89 meters per second squared. If the car negotiates too slowly, as we said before, it tends to slip down, otherwise it tends to slide up. Now they want us to calculate the speed of the car. So to calculate the speed of the car, we can go back to our relationship. The acceleration centripetal is equal to velocity squared by r. We're going to solve for the velocity. So when we factor out, the radius to the other side, so we have radius times the acceleration centripetal is equal to v squared. We take the square root of both terms. We end up with RAC square root. That gives us 316 meters times 5.89 meters per second squared. That's the value of the we solved for in the last part. We get a speed of 43.1 meters per second. So both banking and friction assist in keeping the car on the track. Okay, a racetrack then is said to have a bank curve with a radius of 645 meters. What should be the angle of the bank if the normal force alone is to allow safe travel around the curve at 58 miles per hour? So we're changing the angle and the speed here. So again, we go back to our relationship. The acceleration centripetal is equal to v squared divided by r. We can solve then. We have 58 given, 58 meters per second given, and the radius 245 meters gives us a value of 13.73 meters per second squared. So that's the centripetal acceleration. Now, using that, we can solve for the bank angle. So the acceleration centripetal divided by gravity gives us a value that we can set equal to the tangent of theta, and that is 1.4. So the inverse tangent of 1.4 gives us a bank angle of 54.5 degrees. All right, when we come back, a little more complex problem here with centripetal acceleration, where we look at a roller coaster moving around a circular loop of radius